Greetings everyone, my name is Ray, and in this video, my colleagues and I are going to be teaching the concept of torsion deformation and the torsion formula. So the basic definition of torsion is that it is the twisting of an object with applied torque. And this can be illustrated by this picture of Chris Hadfield on the International Space Station in 2013, wringing out a water-soaked towel with his bare hands. So let's imagine that this towel was originally in the shape of a perfect cylinder with straight longitudinal lines running across its outer face from one end to the other. And now as torque is applied on either side or both ends, these lines become bent, which basically proves the deformation or the twisting of an object with applied torque. So now that you understand the basic concept of what torsion is, my colleagues will be going over the mathematical concept of torsion through the torsion formula, maximum shear stress, torque, polar moment of inertia, and going through some examples.
The torsion formula. The torsion formula is the equation that relates the internal torque to the shear stress acting on the cross-section of a shaft. The equation consists of four different values. Tau max, which is the maximum shear stress on the shaft, T, which is a torque on the moment on the shaft, J, which is a polar moment of inertia, and C, the outer radius of the shaft. Maximum shear stress. When a shaft is twisted or subjected to a torque, it creates a shearing stress. As we go further away from the midpoint, the shear stress increases, and on the midpoint the shear stress is 0. I can also find the shear stress using the following formula, where F is the shear force on the member and A is the cross-sectional area of the member. Torque is basically a type of moment that twists a member about its longitudinal axis. Engineers need to learn about torques and their effects to members to properly design axles or shafts that may be used in vehicles. Shear stress is formed in shafts because of torque or torsion. Torque can also be considered a moment about the longitudinal axis, which means we can use the respective formula where m is the moment or torque about the longitudinal axis, F is the shear force on the member, and D is the perpendicular distance of the force to the point of interest. The outer radius C, the distance from the middle of the shaft where the shear stress is 0 to the outside of the shaft is really important. For instance, if we have a hollow shaft, we might be interested inside the shaft. If we move further away from the middle of our distance, C would increase, which in result will increase the shear stress. Polar moment of inertia. While the area moment of inertia tells us how resistant a beam is to bending, polar moment of inertia is the resistance of a shaft to torsion or twisting. The bigger the polar moment of inertia, the lower the value of shear stress. Polar moment of inertia can be calculated by using the following two formulas. For solid shaft, J is the polar moment of inertia and R is the outside radius of the circular shaft. For hollow shaft, RO is the outside radius of the circular shaft and RI is the inside radius of the circular shaft.
So let's see if we can better understand torsion through this example shown here. We have a shaft subjected to the following external torques. 42.5 kilopound-inch, 30 kilopound-inch, and 12.5 kilopound-inch. And we want to find the max shear stress along section AA. So what do we know? We know that it's given that the diameter of the shaft is 2.5 inches. And if we want to find the max shear stress, we know that it's experienced along the outer surface of the shaft. So in order to find the max shear stress, we have to use this formula. Tau max is equal to torque times C divided by the polar moment of inertia of the shaft. So first we're going to have to cut it along the section so we can find the torque experienced along section AA. We're going to use a very familiar equilibrium equation. The sum of moments along the x-axis is equal to, with respect to the x-axis is equal to 0. We're going to take counterclockwise moments or torques as positive and clockwise torques or moments as negative. 42.5 minus 30 minus t equals 0. and we find out T is equal to 12.5 kilopound-inch. And we also want to know what the polar moment of inertia J for the shaft is. And we know that for any shaft with a circular cross-section, J must equal to pi over 2 times the radius of the shaft to the power of 4. Since it's given that the diameter is 2.5 inches, the radius of the shaft is half that, 1.25 inches. Input that into the formula, and we get that J is equal to 3.834 inches to the 4. So now we just got to input all our values. We know that for tau to be max, for the shear stress to be max, we want C in the formula to equal the radius, because that is the distance from the center, from the x-axis we made here, to the outer surface of the shaft, and that distance is 1.25 inches. Therefore, tau max is equal to 12.5 kilopound-inch times 1.25 inches divided by 3.834 inches to the 4th, and we get that tau max is equal to 4.075 kilopounds per square inches. And we could just convert that to KSI. So the final max shear stress experienced along section AA of the shaft is 4.075 KSI. Let's look at another example. Here we have another shaft subjected to the following forces this time. Torques aren't given here. We're going to have to find out the torques this time, given the forces shown below. And we want to find the max shear stress along section C. It's also given that the shaft is fixed along point A. So the shaft is only twisting along the B end of the shaft. It's also given that the shaft is actually hollow, and it has an outer radius of 60 millimeters and 35 millimeters respectively. Outer and inner radius, respectively. So we want to find out the max shear stress, and we know that the max shear stress is experienced along the outer surface of the shaft. And just like last time, we're going to use the formula tau max is equal to torque times C, which we're going to make our radius, if you haven't realized yet. And we're going to divide that by J, our polar moment of inertia. So, just like last time, we're going to have to cut it at section C so we can find the torque experienced at section C. And again, we're going to use very similar steps like last time. We're going to use an equilibrium equation to find out what T is using the sum of moments is equal to 0. Because external torques are not given, we're going to have to multiply the external forces by the distance from the x-axis we made here. We're going to use a very similar formula for the polar moment of inertia because it is a circular shaft. However, it is not a solid shaft, it is actually a hollow shaft. So we're going to have to, the formula will have to be pi over 2 times the outer radius to the power of 4 minus the inner radius to the power of 4. And we get that J is equal to 1.8 times 10 to the negative 5 meters to the 4th. So now we have everything. We just got to plug in our values into the formula to get the max shear stress. Again, C has to be the distance from the x-axis or the center of the shaft to the outer surface of the shaft, which is 0.06 meters. Plugging all these values in, TC over J, we get tau max to be 133,333 newtons per meter squared. And we can convert that, and our final answer for max shear stress is 0.133 MPa. And hopefully this insight helped you understand all these concepts, and good luck in all your torsion-related endeavors.